Welcome to class 3. We'll continue with elementary reactions. So far in the class, I didn't really make a distinction between reactions and elementary reaction. So according to the UPAC Gold Book, an elementary reaction is a reaction for which there are no reaction intermediates or that have been detected, or they are needed to describe the chemical reaction on a molecular scale. They are assumed to occur in a single step and to pass through a single transition state. So in some books, they use different notations. So they will, for example, reserve only this arrow for elementary reaction, and they use an equal sign for other types of reactions, right? Which is kind of confusing, I think, because you would get something like A equals B, which would be a non-elementary reaction that proceeds from A to B. I find it personally too close to the equilibrium notation, so I'm not going to change that, but officially it's encouraged to make a distinction between those cases. So why does this matter? One thing which is nice is that for an elementary reaction, let's say A goes to B, and I look at the rate, K, so it's K times A. So we said before, there's always some kind of coefficient. So for elementary reactions, that coefficient is the same as the stoichiometry. So in this case, we have 1, then P will be 1. So you can reason, if you know that the reaction is elementary, then the stoichiometry equals the reaction order in A or whatever other species. But the other way around, so if you measure the reaction order and it happens to be equal to the stoichiometry, it does not automatically mean that this is an elementary reaction. Okay, so you should not presume that this is always the case. But okay, like I said, I find this notation quite confusing, so I'm going to stick to the normal arrow for reactions. But it's just something to keep in mind that when you draw a reaction, it's not always elementary. For example, let's say if we look at the hydrolysis of alkyl halides, let's draw it like that, plus water. Some people would write it like that, right? Plus H plus X minus, right? So this, as you probably know, is an SN1 reaction. So it proceeds in 2 consecutive steps, right? So you have first the alkyl halide that splits into 2, and then you have the reaction with water that will give ROH plus H plus. So here, again, notice the notation. This would be that reaction, and these would be elementary reactions split out. And here you can use different arrows. Some people will use maybe a double arrow. So it's encouraged to use this distinction. If you go into very difficult reaction mechanisms, this might become of importance for you, but for the moment I'm going to stick to the normal arrow for reactions in general. So more in general, let's talk about reactions in series, or if you want to say it nicer, you can call it consecutive reaction processes. Okay, so let's say we have 2 reactions. We have A goes to B, and B goes to C with K1 and K2. Okay, so let's look at the rates. Okay, so I have disappearance of A versus time is K1 times concentration of A, or in our other notation, minus dA minus X, right, where A is the initial concentration, K1 A minus X, and X is the concentration at a given time. Okay, so for that we know that the concentration of A will be A times exponent minus K1 times T. For B is being formed, right? So we have dB dt will be K1 A minus X minus K2 times B. Okay, so I just copy in the first reaction B is being formed, so it's the same as minus A, and in the second reaction B is converted to C with the rate K2 times B. Again, I'm assuming here that these are elementary reactions. So let's simplify that. Minus K1 times T minus K2 times B. Okay, so then we can write dB dt equals, plus K2 times B equals K1 times A times E minus K1 times T. Okay, so we have initial conditions. B, concentration of B equals 1 at time is 0. Okay, so if we, for the moment, we assume that K1 and K2 are not equal, then the concentration of B will be A times K1 over K2 minus K1 times E minus K1 times time minus E minus K2 times time. Okay, so how do you now get the concentration of C? For that, we can use conservation of mass, right? So you will always have that the sum of all the concentrations is the same, is constant, and it's equal to the initial concentration of A. So if we substitute that, we get concentration of C is A times 1 minus K2 over K2 minus K1 times E minus K1 times time minus K1 over K1 minus K2 times E minus K2 times time. So I'll try to sketch the progression of such a reaction. Okay, so here we'll put the concentration of the species normalized by the initial concentration. So we start at 1 and we finish at 0 for certain times. Okay, so clearly if we, let's give some color, A will be black, so A, the concentration will drop, will drop over time, right? So this will be A. B will come up and then it will go down and fade away again, because B is really an intermediate. And C will have some induction time, and then it will grow and it will end up at 1 eventually if the reactions are irreversible. Okay, so there's a maximum of B, sorry, T max. Okay, so what's interesting, so this T max, we can derive it from this equation, right? So if we bring this here, and if we take the derivative of that reaction, right, because the derivative of B is 0 at that point, at the maximum point. So we basically set that whole thing to 0. And from that we can see that T max equals 1 over K1 minus K2 times the ln of K1 over K2. So this is an easy analytical equation to look at the maximum amount of B that is produced when you have a reaction in series. So let's continue with parallel reactions. Okay, so let's say we have A that goes to B, and A can also go to C. K1, K2. Okay, so minus dA dt will be K1 times A plus K2 times A. Write it like this. Oops. Okay, so let's again say that A at time 0 is A, and concentration A, is A minus X. So then the integrated form will be ln A over A minus X, K1 plus K2. Okay, so let's assume that initially concentration of B is 0, and at time t we'll call it Y, and at time infinite we'll say it's B. Okay, so if we do that, dy dt is K1 A minus X. However, B must be equal to A when multiplied by K1 over K1 plus K2. Since this is the fraction of molecules A that will react by the first reaction to yield B, and the fraction K2 over K1 plus K2 to react according to reaction 2 to give you product C. Okay, so let's see what that results in. So we have dy dt is K1 times K1 plus K2 over K1 times B minus that times Y, which is K1 plus K2 B minus Y. So integrated ln B over B minus Y is K1 plus K2 times time. Okay, so what's the interesting thing here? So if you do a kinetic experiment, you can, from the yields of the reactions, you can get the ratio of K1 and K2. So K1 over K2 will be the yield of product B over the yield of product C. So this is a way to both determine K1 and K2 from such a reaction. Okay, so let's, these are parallel reactions that are both first order, right? So let's consider case 2, where they are not just first order. So we have A going to C with K1 and A plus B going to D with K2. So the reaction rate dA dt is K1 times A plus K2 times A times B. So we have K1 plus K2B times A. So if reaction B, if the concentration of B is in large excess, right, then this reaction 2 will follow up pseudo first order with a rate constant equal to K2 times B, right? So in this case, this parallel reaction will be similar to the one before, but K1 and K2, they can be determined individually from the manner in which the pseudo first order rate constant equal to, so the pseudo first order rate constant will be K1 plus K2 times B, and how that varies with the concentration of B. So a reaction that you can think of is the hydrolysis of an alkyl halide, Rx, like we've seen before. So in some conditions, you can both have an SN1 or an SN2 mechanism. So it's necessary to measure the pseudo first rate order constant K accent. And when you plot that versus the concentration of base, then the interception at 0 base concentration is the rate constant for the SN1, and the slope is the rate constant of the bimolecular process, so the SN2 reaction. So let's look at a particular case of a consecutive reaction where we're going to make the steady state approximation. So we're again consecutive reaction, and we have an intermediate I. Okay, so we have A that goes to the intermediate, which continues to the product. Okay, so we can again quickly write rate constants. for A, for I, minus K2 times I, and for the product. Okay, mass balance, right? Concentration of A plus that of the intermediate plus that of the product will be the same as A0. So we can integrate all of these as we've done before. Minus K1 times T. I will be K1 over K2 minus K1 E minus K times time minus E minus K2 time times the initial concentration and that of the product 1 plus K1 E minus K2 time minus K2 times E minus K1 time over K2 minus K1 times the initial concentration of A. Okay, so two specific situations. What if K2 is much faster than K1? So there's a rate limiting step. Then P simplifies simply to this. Okay. The other very common assumption is what's called the steady state. Steady state approximation. Okay, so you say that the intermediate stays constant after a certain induction period. Right, so it's like saying di dt is roughly 0. So what happens if we look at this equation where we set this approximation? We say the I dt is K1 times A minus K2 times I is roughly 0. So I is K1 over K2 times A. Right? And then for the product, dP dt is K2 times I is K1 times A. Okay, so we know from here, right, that dA dt is minus K1 times A, okay? And the integrated form, just to remind you again, is A0 times E minus K times T. So if we now put that in here, go to another page, dP dt is K1 A0 e to the minus K1t. So I just substituted concentration of A for the integrated form. P will be K1 times A0 integral from 0 to time t of minus 1k dt is 1 minus e minus k1 times t times a0. So the concentrations for that, roughly speaking, right? So the concentration of A will drop. That of I will increase, and then it reaches this steady state, right? So this concentration becomes constant. So di dt is about 0, right? And then the product P eventually will increase. So this is a very common approximation that is used. Okay, let's continue with equilibrium, simple equilibrium. And I'm going to approach it a little bit different than probably it's introduced, right? So the interesting part is the equilibrium position, determining the eventual position of the concentration. So let's say we have species A in equilibrium with species B. We have a forward rate K1 and a backward rate K minus 1. Right, so let's take again the initial way we do things. So A at time 0 is B, or sorry, it's A, small letter A, and B is X. That's the unknown value. And so we'll write dx dt is K1 A minus X minus K minus 1 times X. And at equilibrium, these rates are balanced, right? So there's the overall change at equilibrium dx dt equals 0. Okay? So what's the equilibrium concentration of B? That is, let's call that the equilibrium XE. So that's the equilibrium concentration of B. Okay, so let's see what that is then. So we will have K1 times A minus XE equilibrium equals K minus 1 times XE. So let's work this out. K1 times XE will be K minus 1 times XE. K1 times A is K1 plus K minus 1 times XE. Okay, so we substitute that. Dx dt is K1 plus K minus 1 times XE minus K1 times X minus K minus 1 times X. Okay, is K1 plus K minus 1 XE minus X. Okay. So let's integrate that from 0 to x, dx of xe minus x is k1 plus k minus 1 integrate from 0 to t equilibrium dt. Okay, so that will be ln xe minus ln xe minus x equals k1 plus k minus 1 times t equilibrium. So ln xe over xe minus x is k1 plus k minus 1 times t equilibrium. And then maybe the more normal way of writing things, if we go maybe a bit back, is that you have, the big K, capital K, the equilibrium constant, will be concentration of B, equilibrium over that of A at equilibrium, which is the ratio of K1 over K minus 1. In general, if you have coupled equilibria, K will be minus A times. So this is if you have a series of coupled species, right? That's the more general way of writing things. Okay, so let's move to a small exercise. So a tip for that exercise is, using the derivation that I just gave you, you can say something about the rates. So how fast is the equilibrium established if I go from one direction to the other? Let's say I start with all A and I go to B. There's a certain rate at which the equilibrium is achieved, but also the position of the equilibrium. So the final concentrations of the two species tells you something about the ratio of the rate constants, right? So that is this result and this result.